Hi folks, and welcome back to another episode of Starting Sciart. It's episode 2. Today we'll cover how to illustrate different aspects of electrodes in lithium-ion batteries. We're going to be covering quite a lot of ground, broadly looking at 3 points. First, we're going to make together a really basic electrode schematic, which consists of your basic elements and active material, together with representative elements for the conductive additive and binder. I'll also show how you can make this kind of schematic electrode in which the active material is surrounded by another phase, which could be useful if you work with, say, solid electrolyte batteries. Finally, we'll look at some illustrations looking at battery degradation, so how you can illustrate active material with cracks, and maybe adding coatings of SEI or solid electrolyte interfaces to your active material. Since we're going to look at quite a lot of things, I'll leave timestamps for each of the 3 sections in the description box. Before we start, I just want to point out that we'll be working with the Cycles render engine, as we'll be making use of point clouds which don't work in Eevee. Starting from scratch in an empty scene, we're going to first need to add ourselves a current collector. So let's just simply add a cube, scale him down in both the X, Y, and the Z direction. And let's go ahead and rename this guy a current collector. Open up the shader editor and let's create a new material, again called current collector. Give him a metallic color, up the metallic, and drop the roughness. I might also add a bevel modifier. So come to the modifier tab, add modifier, bevel. This is a great point to remind everyone to apply scale by pressing Ctrl A and scale after you've rescaled elements. And let's go ahead and right click and shade smooth. Come to the data properties for the object, down to normals and select auto smooth. And we have ourselves a reasonable looking current collector. So to be able to create all of the active materials and dispersed binder and conductive additive, we're going to do everything in geometry nodes. So let's go ahead and open up the bottom work page. Make that the geometry nodes editor. The first thing I'm going to do is add another cube, scale them down. Not that that hugely matters, but I will call this the electrode material. And let's create a new node tree. Let's call this electrode type basic, as this is going to be our basic electrode setup. So let's first work on the active material, which involves distributing a bunch of spheres. Let's first distribute a number of points on which we can instance those spheres. We're going to first convert the cube into a volume. So go ahead and look for a mesh to volume node. Let's drop the exterior bandwidth to something small, like 0.01. And you then want to look for a distribute points in volume node. If I now crank up the density, you can see that I've got a bunch of points. Let's go ahead and look for a instance on points node, and into the instance object, let's first add a set material node, and into the geometry, look for a points node. And so now all I've done is distributed a bunch of points in the volume of that cube. If I just quickly come to rendered view, this is how it looks. So it's just a bunch of spheres floating in air right now. So we're going to need to do a little bit of work. First thing we need to do, I'm going to change from random to grid so that we get a regular array of spheres. And we're actually going to start with this and then mess them around by moving them according to some noise. Drop the radius to something smaller, something like 0.05 maybe. I'm also going to add a value node to the spacing. So just have a single float value to drive the spacing between these spheres. If we go with something like 0.1, that gives us a very dense array of spheres. What I can do is make this entire layer of spheres a bit shorter, and do that by coming into edit mode for the cube, press S and C to scale, and just scale it down in the Z direction, and then bring this all down. Let's go ahead and make an active material by coming to the material properties tab, and let's make a new material, call it active material. Let's give it a bluey color. Just for fun of it, let's make the metallic all the way to 1 and drop the roughness a little bit. Come to the set material node and select active material. That's looking extremely shiny. Let's maybe actually increase the roughness. I'll make it something like 0.8. So now we have ourselves a regular array of active material particles. These could be nanoparticles, these could be hierarchically structured microparticles, whatever you want. So we're going to do 2 things. First, to sort of make this a little bit more realistic. First, let's apply different sizes to these spheres so that they're not all of uniform size. Come to the scale input for the instance on points and look for a random value node. Set the type from vector to float. You might have to reconnect after that again. And so this basically chooses a random scale for each of the points between 0 and 1. We don't necessarily need the random value to be selected all the way between 0 and 1, maybe a smaller range like say 0.7 to 1, maybe something even more, 0.6, right? And now we get a distribution of sizes. The next thing we're going to do, we're going to displace all of these particles. To do that, set the position of each of these points using a set position node, which we plug in after the distribute points in volume. So we're going to set the position of all of those points before instancing those spheres on those points. You're going to want to look for a noise texture, a position node. Let's have a vector math node set to add. And you're basically going to take the position of each of those points and add a noise value to it. So displacing it by a certain noise amount. If I then take that and plug the output of the add value into the position, you'll see that I've managed to displace all of those points. All of them are currently offset diagonally upwards. This is actually adding a 0.5 in X, Y, Z directions. So we actually need to subtract 0.5 and that should recenter all of the points. The next thing I'd like to do is be able to scale the amplitude of displacement. So what you're going to want to add is a vector math node and apply that after the subtraction. Convert that from add to scale, and now the scale value allows you to control the strength of the displacement. Other things you can play with are, for example, the roughness of the noise. You can also change the scale of the noise texture. So if you make the scale bigger, you'll have much greater period noise textures, and you can also apply distortion and various other things. So you can achieve a active material distribution that you are looking for. In this case, this is looking a little bit too clustered together. So what I will do is maybe increase the scale of the noise, crank up the detail. Something to be careful of is the inputs for the spacing for the distribute points in volume can be easily made too small so that you have too many points in Crash Blender. So make sure you don't unnecessarily make this value too small. But this is looking good enough for now. I mentioned at the start that you don't necessarily have to use spheres. You can instance whatever you want on these points. If you wanted to instance something other than spheres, let's say you make a non-spherical active material particle. So here, for example, I made a weird looking particle, something that isn't necessarily spherical, from an icosphere, and I could equally take that and distribute them here instead of the points. All I would have to do is connect rather than the points. I would look for an object info node, take its geometry output and plug it into the geometry for the set material, take the eyedropper, select that object, and there you have yourself the material. Now you might have to again tweak the scale value so that you have a more reasonable looking active material distribution. Okay, so I would scale this initial particle in size. Something you'll notice here now is that since we have something that is not necessarily spherical, that all of the instances are aligned, all pointing in the same direction, which doesn't look particularly nice either. So you could add a random value to the rotation of the instance on points. And this time we keep it at vector and we need to select a random rotation between 0 and 2 pi for the XYZ components. And now we have something a bit more realistic looking, a bunch of faceted active material particles instead of spheres. So you can plug in whatever you want for whatever shape of active material particle you desire. So just coming back briefly to spherical active particles, the next thing we want to do is distribute a bunch of points of, say, conductive additive around these particles. For demonstration purposes, this actually works much better by adding a icosphere instead of a point. Let's give the radius the same value as for points and just plug that into the set material node instead. So now we're instancing a bunch of icospheres. Let's up the subdivision. You don't have to go too crazy, maybe something like 2. And let's add a set shade smooth node for the set material node so that we have a bunch of smooth spheres. Now to instance a bunch of particles on the surface for conductive additive, I'm going to first realize instances so that I actually have some mesh to work with rather than just instances of these spheres. I'm going to take those realized instances and apply a distribute points on faces node. I just plug that into the output, join that with the original geometry. What you should find is that we now have a bunch of points distributed on the surface of those original points. This is quite difficult to see as both of them are spheres. So let's go ahead and add an instance points after the distribute points and faces. Let's add a set material with the instance socket as well as a points node. And so these points, let's say, are going to be our conductive additive. Let's scale the radius down, something smaller. Let's create a new material, the conductive additive. Let's make it black to signify something like carbon, and select conductive additive here in the set material. If I come into rendered view, here we now see some of the conductive additive particles distributed on the surface of the active material. If I take the density value of the distribute points from faces and just crank it up, I can add more or less of these particles. If you wanted these particles to sit actually on the surface rather than sort of sitting half embedded in the active material, just add a transform geometry node just before the distribute points on faces, plug a value node into the scale input for the transform geometry and set it something slightly bigger than 1, like 1.02, and that should allow you to make the particles sit further onto the surface like so. So here's how the node tree is currently looking. Let's tidy up some of these nodes for good housekeeping. So all of these nodes on the left, these are responsible for making the active material. So go ahead and press Ctrl J to make a frame. Let's call this frame active material. Likewise, the nodes here, I've used the join geometry to connect with the original geometry. Let's frame together and call this the conductive additive. Last step is to create the binder material and distribute those as well using a very similar method to what we did for the conductive additive. For that, I'm first going to need to add a Bezier curve. Let's make the Bezier curve a little bit smaller. Let's just displace them in the X direction. And I'm going to call this the binder. Click on the electrode material again, and you're basically going to want to duplicate all of the stuff we did for the conductive additive. So select all of that. Press Ctrl Shift D, duplicate with connections. And now instead of the points here, I'm going to want to use this Bezier curve to create the squiggly little chains that will represent our binder. So into the geometry, look for an object info node, take the eyedropper and let's select the binder. This is now currently just instancing curve, so we need to convert that to mesh. So let's add a curve to mesh node, plug it in after the object info. Into the profile curve, let's look for a curved circle and set the radius to something much smaller. Now we need to take the output of this instance on points for the conductive additive and also plug that into the joint geometry. You can see that binder is way too big, so let's go ahead and scale some things. Let's first actually scale the original Bezier curve, something much smaller. Press Ctrl A to scale, and that should give you something a bit more manageable. Some other things I need to do, I can also play with the scale here on the instance on points. I'm going to add a value node here and let's set it to something like 0.5. So now that looks a little bit more reasonable. All of these binder chains are currently open-ended cylinders. So I want to press fill caps to make them solid. And just like we did for the icosphere active material where we changed the rotation of each of the elements, we're going to want to do the same. So from the rotation input on instance on points, let's look for a random value node. Again, keeping it vector, let's make this 2π. And so now we have random rotation everywhere. Now you might notice that where we have a binder particle, we also have an active material particle. That is because we copied over the exact same distribute points on faces node. And so it's distributing literally on the same points, both binder particle and conductive additive. That is easily remedied by just clicking on the seed value for one of them. So I'll choose the binder. And so now these should be sitting on different points. Let's just have a quick look in the rendered view. Let's make ourselves a different material for the binder. Let's add a new material, binder material, and let's give it a distinctive color, maybe something like yellow. Let's select that. And so now we have a bunch of binder particles distributed around the active material as well. Again, as with the conductive additive, I can increase or decrease the amount of this stuff by just changing the density. And I'm going to bring this a little bit down so we don't have quite as many binder particles distributed. And so there we have the beginnings of an electrode material, just a really basic one. Now let's consider the case when we want to make the volume filled version. We're going to take a slightly different approach. We're actually going to use the making porous materials tip that I have a separate video for, in which we use the volume cube to make a porous material. And we're going to use that to either define the positions of the active material or the inverse to define the position for whatever you want to fill in between. Add a new cube to the scene, and let's just repeat the process of scaling it down and slotting it on top of the electrode. All of this doesn't particularly matter as we are going to convert this cube now into a volume cube. So with the cube selected, let's now create a new node tree. And so the first thing we're going to do is disconnect the cube input and look for a volume cube. All I'm going to do now is actually just repeat all of the steps that I outlined in the previous video on making porous materials. I'll put a screenshot of the node setup that I'll recreate. Just pause the video and create the setup. So once you created this node setup, you should have something that looks like this, just a porous looking material with a bunch of globular particles, which will serve as our active material, and we're going to now fill the gaps in between. So first, let's make the minimum set to 0, and let's now play with the bounds so that we have something that sits properly on the current collector. Let's make both the minimum, the x and y, to 0.5, and also the max to 0.5. Let's bring all of this down so that it sits on the current collector. Let's also drop the max in z to 0.5 as well. So in this situation, the scale of these particles is now a bit too big. We've ended up with loads of space in between. So we can remedy that by cranking up the scale. And now we have our active particles. One last thing to do, let's set the material to this. Let's add a new material. We'll call this active material 2. Give it a different color to the previous one, something like this. Change the material to something probably metallic. And for this setup, let's change the current collector color to something silvery. So the operation we're looking for is to basically find the gaps in volume where we don't have these particles. So we basically need to take the volume cube density and invert it. So the way we do this is we basically just need to do a 1 minus whatever value we're currently plugging into the density. Let's duplicate all of these nodes. Press Ctrl-Shift-D to keep the connections and duplicate. And then let's add a math node, plug that in between the color ramp and the second block of nodes we've just created. And we basically want to do a subtract operation and take 1 minus whatever density distribution we're driving with this texture. If we now take the output of that, join it with the output of just the active material part of the Voronoi texture, we should end up with a complete volume cube, though there are some pinching effects happening where we join them together. What we now want to do is use this surrounding volume to instance further points. So here, rather than using a volume to mesh node, I'm going to delete these two things, and we're going to use this volume to instance a bunch of points. So distribute points in volume. And again, we want to add an instance on points node. Let's crank up the density and plug in points with a radius of say 0.01 into the instance socket. If you're finding that the points are too sparse, you can of course play with the density, but also the density that we plug into the volume cube by changing the max of the map range node. Let's change the radius to something a bit bigger. Let's join back in the active material particles into rendered view. And now we can see we have a bunch of smaller particles surrounding the particles of active material. So now it's just a matter of optimizing to get the look that you want. Maybe you want a bunch of small particles, in which case you're going to really need to crank up the density as well as the density input of the volume cube. Make sure that you've properly fill in. Add a set material node after the points for the smaller spheres. Let's create a new material, and I'm just going to call this filler particles because this could be whatever you want. Could be solid electrolyte, could be other materials that you put in the electrode. So here I just made it black to make it quite easy to see, but that is basically the complete effect. For the final part, I'm just going to come back to the original set of electrodes that we created with instancing particles and conductive additive and binder. And so let's now say maybe we want to illustrate an SEI layer forming on the surface of all of these active material particles, or maybe illustrating cracking active particles. So for the case of an SEI forming, you could obviously surround each of these individual spheres with their own SEI layer. In this case, I'm going to show a different way in which you can basically just wrap the entire bunch of active particles with a layer. We are first going to convert mesh to volume. So we're basically converting all of these realized instances of spheres into a volume first, and then we're going to convert that back to a mesh. So volume to mesh. And if I just plug that into the join geometry, you'll get yourself this sort of puffy looking surface, which is kind of what we're after. First, drop the exterior bandwidth to something smaller. Let's set shade smooth. And now what we basically have is a coating that just covers or wraps around all of the active material. Add a set material node after the shade smooth and create an SCI material. For illustration purposes, I'm just going to crank up the transmission to 1 and keep the roughness quite high, like 0.4. And let's just select that. If I come into rendered view, you'll see that we basically just created this film material that coats all of the active material particles to maybe illustrate the SEI. If you wanted it to be thicker, you can always put back the exterior bandwidth value to make it sort of blow out a bit more. In the illustration I showed at the very beginning for the thumbnail, I only have part of the active material covered with this SEI. To do that, you just need to delete some of this layer away by using a delete geometry node. Set to point. Let's create an appropriate selection of just half of the layer. Look for a compare node in the selection. Set it to float. Look for a separate XYZ. And plug in a position. Where the X value for the position is greater than a certain value, I want to delete it. And so now you have a procedural way to slice open the SEI layer to reveal the active material. The SEI doesn't have to be transparent. You can give it a solid color. Let's give it a random material and just bring down the transmission. If you wanted to give it some thickness, you could also apply an extrude mesh, set to individual, and bring down the offset scale. Right, and now we can apply a little bit of thickness rather than just a thin layer. And so there are many options possible to create your SEI layer to wrap around the entire active material layer. One more thing, which is a bit of a tangent, but if I wanted to illustrate, say, one of these active material particles undergoing degradation, so maybe it's cracking, perhaps I wouldn't illustrate it here within this figure, but I might show an inset figure with a sphere all cracked up. So I'll just quickly show how you can do that. I'm just going to add a cube. Add back in our solid electrode node tree, and let's delete the bottom half for creating the fill-in. We're just going to use this. Now what we want to do is recreate the cube. Let's change back to minimum of -1 in all directions and +1 in the max. Rather than the volume effect happening in a cube, we need to constrain everything in a sphere, and also we need to change the texture that creates the cracking effect. So let's do the latter first. In the Voronoi texture, go ahead and look for the distance to edge option and let's play around with the color ramp. Let's bring in the black a bit as well as the white. Right, and so now we have ourselves what looks like cracked material. And now what we're going to do is, rather than have this as a cube, we want this to be all inside a sphere. What we want is a density value that is 1 in a sphere. We can do that by taking the position value. Let's add a vector math node. Rather than add, let's compute the length of each of the position points in the volume cube. And what we want to say is compare that to some kind of value, some float value. And where it is less than or equal to that value, I want the density to be 1, and otherwise I want it to be 0. Take a Boolean math AND node, plug in the output from the texture into the other socket of the Boolean, and plug that into the map range node. And so the result of that is this cracked looking sphere. If I come into a rendered view, you can see we basically created what looks to be a fairly convincing ball of atom material that is now cracked throughout. Again, if you wanted to increase or decrease the size of each of these cracked pieces, you can play with the scale. So if I increase the scale, you might find that the particles get smushed together, so you would need to play with the color ramp again to get the desired sort of particle effect. The smaller the scale value, the larger the particles. So if I set the scale to something like 2, I'm toggling the color ramp like this, let's say. Now we have bigger domains to create our cracked shards. And so that's basically the 3 points I wanted to cover today. Please leave a like and a comment if you found it useful, particularly suggestions on different kinds of walkthroughs that you'd like to see in this series. Subscribe for more content, and I will see you all next time. Bye bye for now.